Okay, welcome everyone to week 9 of the problem solving session or the tutorial session of the course Control Systems. So today we'll be solving problems on Bode plot, and we'll start with some basic problems, and then the next week we will see some good problems on Bode plot. Before that, okay. In the last session, we solved this problem where we were given open loop poles at the location 0, -1 and -2. Okay, and it was given that the root locus of system transits to unstable region at frequency equals to k, and then we introduced a 0 at -3 in open loop transfer function. Okay, and then we have to identify the correct option. Okay, so by solving it, we calculated the asymptotes. So number of asymptotes for the previous case will be equal to 3 because we have poles at 0, -1 and -2. So n equals to 3 and m equals to 0, that is there is no zeros. So the number of asymptotes were 3 and angle of asymptotes were this. And it correctly shows that there is a gain k where the root locus will transit to this right half plane. Okay, so that will make the system unstable. In another case where we have 1 0 at -3, so what we did was, let's solve this part again. So now in this case, we have zeros at we have poles at 0, -1 and -2, and then we introduced a 0 at -3. Okay, and we are asked that is there any gain such that we transit to unstable region, that is to the right half plane. Okay, so we correctly identified the real part of the axis where the root locus will lie. So from here, since at this point the number of poles or zeros is even to the right of it, so this part of real axis and this part of real axis will lie in the root locus. Okay, then further we calculated number of asymptotes, that was n minus m, which is 3 minus 1 in this case, that is 2 asymptote, and it is also logical because one branch will start from this open loop pole that is at -2 and will converge to the open loop 0, -3. So this branch will have no asymptote, so the asymptotes will originate from these two pole locations. Okay, and then we calculated the angle of asymptotes, which was 90 degree and 270 degree. Okay, and what we concluded that these the branches will break out from here, and then the asymptotes will make an angle of 90 degree and the another will make an angle of 270 degree. And we concluded that this root locus will never cross the imaginary axis, and hence it will never go to the RHP. But the point to take care is that the angle of asymptote, which we got as 90 degree and 270 degree, that doesn't mean that it break out at an angle of 90 degree or 270 degree. These angle means that it is the angle of the asymptotes, means at k tending to infinity, the asymptotes will make an angle of 90 degree and 270 degree. So it can happen in the way that it is possible that the asymptotes, so it is possible that the branch will break out from here and it will go like that, and then further it will make an angle of 90 degree and 270 degree. Like this it can happen also. So this angle will be 90 degree and this asymptote will make an angle of 270 degree. So if that is the case, then the root locus will intersect the imaginary axis and it goes to the RHP. Okay, so by calculating only the angle of asymptotes, we cannot conclude that our root locus will never go to RHP. So if that is the case, then one thing that we need to calculate is the point at which the root locus intersects the imaginary axis. Okay, so then we will see how our root locus will behave. Okay, so now let's see. Okay, since we have the open loop transfer function as k into s plus 3 divided by s into s plus 1 into s plus 2, because it is given that we have open loop 0 at minus 3 and open loop poles at 0, minus 1 and minus 2. Okay, then the closed loop transfer function will be, or we can directly write the characteristic equation, because we need to solve the point at which the root locus intersects the imaginary axis. So the characteristic equation will be s into s plus 1, s plus 2 plus k into s plus 3, right? And to identify the point at which it intersects the imaginary axis, that means the real part is 0. So what we have to do, we have to put s equals to j omega, put s equals to j omega here. Okay, okay, so if I put j omega, it will be j omega plus 1, j omega plus 2 plus k into j omega plus 3, and this equals to 0 because it is the characteristic equation. Okay, now let's calculate these terms. So it will be j omega and plus k j omega plus 3. Finally it will be minus j omega cube okay, and then we will keep the real parts and imaginary parts separately. So the real parts are minus 3 omega square and plus 3k. The imaginary parts are k omega plus 2 omega minus omega cube equals to 0. Okay, so both the real and imaginary parts we have to equate equals to 0. So this will give us 3 omega square. So we will equate this to 0 and this to 0 individually. This will give us k equals to omega square, and this will give us, if we put k equals to omega square, it will give us omega cube plus 2 omega minus omega cube equals to 0, which means omega equals to 0. So what does it mean? So since k equals to omega square, so k is also equal to 0. So what does it mean? It means the only point at which the root locus intersects the imaginary axis is omega equals to 0 means the only point it will intersect the imaginary axis is the point of the pole location, right? So there are no any other point apart from this pole location that the root locus will intersect. Okay, so it means that our root locus will start from these open loop poles, okay, and then it may break away from any point that you can also calculate, and the asymptotes will be such that as k goes to infinity it will make it will converge parallel to the y-axis such that these asymptotes make an angle of 90 degree and 270 degree. Okay, so the root locus will never go to RHP, right? So the answer was correct, but this thing we also have to care, right? Any doubt in this question, anyone? Okay, another question that we solved was, yes, okay, so this question was related to the state space model, where we have a system and we are representing that system using the state realization given by x dot equals to ax plus bu, and some another person pick another set of states and he is representing the same system using this state space model w dot equals to cw plus du. Okay, so both of these state space models are representing equivalently the same linear system, and the set of eigenvalues for system 1, which is x dot equals to ax plus bu, is given by lambda, and the set of eigenvalues of state space model w dot equals to cw plus du is given by mu. So these things I have written here. Let me clear these things. Okay, so the set of eigenvalues for this state model is lambda, and set of eigenvalues for this state model is mu. Okay, and the question was to select the correct option among these four. So the first option was saying that the set of eigenvalues will be same and or if the states are equal to each other. So if x equals to, so let's see these points carefully. Okay, so for case A, let's say the case A is saying set of eigenvalues are same and the states are equal to each other. So what happen if states are equal to each other? What can we conclude? So x and w are equal, they are same. So what does it mean? They have the same state matrix also, and if they have the same state matrix, that means their eigenvalues are also equal. So this option is correct. Okay, and the second option, it was, so let's call it case B. It is saying that the set of eigenvalues are same but the states are not equal to each other. So what does it mean? It means that someone has chosen set of states as x, and another one has chosen set of states as w, which are not equal, but it is saying that their eigenvalues are equal. So this can also be true, but it can also be not true. So let's see this point. For the case when this will be true is, let's suppose someone has chosen the state x and someone has chosen w as 2x. Okay, so in this case these are not equal to each other, but when you see their state space model, you will find that both a and c will be equal to each other. So that means lambda will be equal to mu, that is the eigenvalues will be equal to mu. So this is the case where this option can be true. But for the case where this option is not true is that, let's suppose someone has chosen states as x, set of, it can be x1, x2, x3, set of states, and w is, let's suppose, just x1, x2. There always exists a minimal realization of not always, but there can exist minimal realization of the system where two states will be enough to represent to tell everything about the system. Okay, so in that case a will not be equal to c, and therefore their eigenvalues will not be equal to mu. Okay, so there is one counter example where this option is not true. Not true always, it can be true but not always. Okay, so option B is incorrect. And third option, so the third option is saying that the states are equal. So if the moment the states are equal, what does it mean? It always means that a will be equal to c and the eigenvalues will be equal, but it is saying that the eigenvalues are not equal, so this option is not correct. And in the last case we have the states are not equal and the eigenvalues are also not equal. So let's see this case. Case T is saying lambda is not equal to mu and x is not equal to w. So what do you think? It is correct or incorrect? Because here we have fixed the states to be not equal. Does that always mean that the eigenvalues are also not equal? No, because in this example we have seen this. What we have seen, we seen that the states were not equal to each other. Okay, but the state matrix were equal to each other, and hence the set of eigenvalues were also equal. So this option is also not correct, because even if the states are not equal, there exists a possibility that the eigenvalues will be equal to each other. Okay, so the only correct option is option A. Anyone having any doubt in this question? Okay, then let's start today's session. Okay, so today we'll be solving problems on Bode plot. Okay, so the first question is what does the y-axis of the magnitude plot of the Bode plot represents? Or what does the y-axis, how we express the y-axis of the Bode plot?
Option B.
Option B, yes. So this is just very basic because it is in the definition only that the Bode plot is a plot between the frequency in the log scale, okay, logarithmic scale we take, and in the y-axis we have the magnitude in dB. So to convert the magnitude in dB, we take 20 log of 10 magnitude of transfer function p. Okay, Okay, which option is not correct about using a logarithmic scale for plotting frequency in the Bode plot? So we know we take logarithmic scale to plot the Bode plot, but why we take it? Or which option is not correct for the logarithmic scale?
Option D is incorrect.
D is not correct. The lower frequency ranges can be expanded. Why it is not correct? D
D,
is
I am
not
saying.
correct. Okay. Okay. So the option number one is a large range of frequency can be represented. So that's the logic behind taking logarithmic speed, because we want to plot for as much frequency as we can, and the log scale allows us to do that because we can represent frequency of 10 to the power 1, 10 to the power 10, starting from 10 to the power minus 10, any value we can go, and that can be represented in just like minus 10, minus 9, and up to we can go to 10 to the power 10 in very uh, and we don't need very large x-axis for that. So that's the beauty of log scale. And similarly, lower frequency ranges we can also represent, because we can represent 10 to the power minus 9, 10 to the power minus 8, etc., etc. So these are low frequency ranges. Okay. And can we represent zero frequency in Bode plot? No, we cannot represent zero in log scale. Can we do that? The scale is like 10 to the power 0, 10 to the power minus 1, 10 to the power minus 2. How low we can go? That will always be some value. We cannot go to, if even if we have 10 to the power minus 100, it is not equal to 0, right? So 0 frequency we cannot represent in the Bode plot. So this option is not correct. Zero frequency cannot be represented in the Bode plot. What about the fourth option then? If point C is exactly halfway between points A and B, the value of frequency at point C is the geometric mean of the corresponding values at point A and B. Okay. Uh, Tell me one thing. If we have a linear scale where we have a point A and B, and then we have a point C in middle of that, and we have a linear scale. So what is the relation of C then? C, what can we write C? Can we write C equals to A plus B by 2? Now, if
Yes.
you have the logarithmic scale, so your points will be log of A, log of B, and log of C. Okay, and it is given that it is in the middle, so log of C is log of A plus log of B by 2. Okay, it is given. Then we have to find the relation between A, B, C. Okay, now take log both sides. Uh, log C can be written as log A B by 2. Can we write it like this? So log A plus log B is nothing but log of A into B, and then you can also see that this is, and this factor can be taken inside log as power. Okay, now we can remove log, so what it will give us, c will be equal to a into b to the power half. That means c equals to under root of ab, and this is nothing but geometric mean. Okay, so the last option is correct. If point C is exactly halfway between point A and B, the value of frequency at point C is the geometric mean of the corresponding values at points A and B. Okay? Okay. So in third question, if a Planck transfer function is expressed as f of s divided by g of s, the magnitude in dB of the Planck sinusoidal transfer function is. Very easy. What will be the magnitude in dB of this transfer function?
I think fourth one.
The fourth one, yes. Okay, so we have a transfer function, let's call it as ps equals to f of s divided by g of s, and in frequency domain we can write it as g of j omega. Okay, and the magnitude in dB is nothing but 20 log of magnitude of p of j omega, and which is equal to 20 log of magnitude of f of j omega and magnitude of g of j omega, and division in log equals to subtraction, so it is 20 log magnitude of f of j omega minus 20 log magnitude of g of j omega. Okay, and base is 10 natural log, so the last option is correct. And what is the angle? What is the phase of the plant? So the angle of this transfer function will be nothing but angle of f of j omega minus angle of g of j omega, because it is in denominator. The third option is correct. Now we are given a Planck transfer function p of s which is equal to minus 20. Find out the magnitude in dB and phase in degrees of the transfer function. Magnitude in dB. What will be p of j omega? N
just
of
minus
omega means
20.
p of j omega will be nothing but minus 20, so it's a constant transfer function. And then what will be its magnitude then? 20. And what will be the magnitude in dB?
20.
It will be 20 log 20, which we can write as 20 log 10 plus 20 log 2. Okay, and this is nothing but 20, and 20 into log 2 will be, it is equal to around 6, you can approximate, so it is 26. So the magnitude in dB is 26. What about phase? Phase you can directly guess, no need to calculate. It's the negative real axis, so it makes an angle of 180 degree. So the phase is nothing but 180 degree. Okay. Find the slope of the magnitude plot. Okay. So
Yes,
what
ma'am.
is the slope of the transfer function uh, p of j omega given as 1 by j omega in dB per octave? So remember that you have to find the slope per octave, it's not per decade. So per decade means there is an increment of frequency by a factor of 10, and octave means there is increase in frequency or decrease in frequency. So if we are saying increase, then there is an increase of frequency by a factor of 2. Okay, so first let's calculate its magnitude. Its magnitude will be nothing but in dB, it is nothing but 20 log magnitude of 1 by j omega. So it is, since j omega is in denominator, we can directly write minus 20 log of w. Okay, minus 20 log omega. Okay, so at omega we have magnitude as minus 20 log of omega. What will be the magnitude at 2 omega? So by octave we have incremented. Okay, so the magnitude will be minus 20 log 2 omega, which we can write as minus 20 log omega minus 20 log 2. We can write it like this.
Ma'am, how this plus 20
Okay,
become minus 20?
so this is what, 20 log 1 plus 20 log 1 by j omega, we can write. Magnitude is just omega only. Okay, not like this. So this is equal to 20 log 1 by omega. Is it correct? What the magnitude of 1 by j omega is nothing but 1 by omega. Now, using the multiplication and division rule, this 1 by omega we can break it as 20 log 1, correct? And minus 20 log omega. And what is log 1? It is 0. So we are left with minus 20 log omega. It is clear to you now? We have just used the rule of division. Okay.
Yes, ma'am. Clear.
Okay. So at frequency omega, the magnitude of P of j omega, it was minus 20 log omega, and at double the frequency, that is, if we increase the frequency by an octave, we got this magnitude. Okay, so by how much we have increased or decreased? So earlier we were at this, so in this case we are equal to this, but also there is subtracted by this much amount. So how much we have changed? We are changed by this value. Okay, yes. So and
Minus
we
6
know
dB.
that 20 log 2 is nearly equal to 6, and we have a minus 6 minus sign here, so it is minus 6 dB. Okay, so the answer is minus 6 dB per octave. And what if it was in decade? What will be the slope if we calculate in dB per decade? Yes, it will be minus 20.
minus 20.
That you can also calculate using this logic. In that case, in case of 2w or 2 omega, it will be 10 omega. Okay. Okay. What is the corner frequency of this transfer function? Okay, so we know that for a first order plant, or first order transfer function, we can say the standard form is 1 divided by 1 plus st, and the corner frequency is given by omega equals to 1 by t. Okay, so this is the corner frequency for first order systems. Now can you find out the corner frequency for this transfer function? So what is t here? It is equal to 2. Then what will be 1 by t? It will be 0.5. Okay, so the corner frequency is 0.5 because t here is 2, so it is equal to 1 by 2, which is 0.5. Okay, find the magnitude of the transfer function as the frequency tends to 0. So the transfer function was P of j omega was 1 by 2 j omega plus 1, right? What is the magnitude as frequency tends to 0 in dB? 0.
0.
Yes. So that's the case for first order plant also, or we can calculate it if anyone wants to see how it is derived. So P of j omega in dB is nothing but 20 log 1 minus 20 log of 1 plus 2 omega square. Okay, this goes to 0, so we have minus 20 log under root of 1 plus 2 omega square. Now if you have omega tends to 0, that means as omega tends to 0 we will have minus 20 log 1 only, and log 1 is 0, so it will tend to 0. So the magnitude in dB if omega frequency tends to 0 is equal to 0 dB. Also calculate the phase for the same transfer function. Let me write the transfer function. What is the phase of this transfer function? At omega equals to corner frequency. So corner frequency we have just now calculated, it was equal to 1 by 2. So at omega equals to 1 by 2 we have to calculate the phase. So for a transfer function we know that the phase we can calculate as phase of numerator minus the phase of denominator. Okay, so numerator is just a constant, a real number, so its phase is 0, a positive number, so its phase is 0, minus the phase of denominator is tan inverse of imaginary part is 2 omega by 1, and omega is given as 1 by 2, so it is equal to minus tan inverse of 1 only, and tan inverse of 1 we know is 45 degrees, so it is minus 45 degrees. The phase at the corner frequency is minus 45 degrees. What is the corner frequency of this transfer function? So again we have to write it in standard form and then calculate 1 by t, because this is also a first order transfer function. How to write it in standard form? So we
We're
have
taking 2 as a common factor.
omega and then multiply with 1 plus s. Okay. So what is t here? It is nothing but equal to 1, because 1 is multiplied with s, right? Then what will be the corner frequency? It will be at omega equals to 1 by t, which is nothing but 1. So for this problem, 2 into s plus 2, p is 2 into s plus 2, calculate in the magnitude in dB as frequency tends to 0. Same problem. As frequency goes to 0, what will be the magnitude of this transfer function? Let's write it in frequency domain first. So it will be 2 omega j plus 2. So its magnitude will be under root of 2 square plus 2 omega square, which is 2 1 plus omega square. Okay, and then in dB it will be equal to 20 log of p j omega, which is equal to 20 log of 2 into under root 1 plus omega square. Okay, so it is 20 log 2 plus 20 log of under root 1 plus omega square. Now as omega tends to 0, this this term goes to 0, so we'll be left with only 1. So it will be 20 log 2 plus 20 log 1. So log 1 is 0 and 20 log 2 is 6. So the answer is 6 dB. So as frequency goes to 0, its magnitude will be equal to 6 dB. Any doubt?
No, no.
Okay, similarly, find out the phase for this transfer function at the corner frequency. So it was 2 omega j plus 2. Calculate the phase of this transfer function at corner frequency. So the angle of or the phase of P will be nothing but, we have only numerator, so it is just tan inverse 2 omega by 2. Okay, and what was the corner frequency for this transfer function? It was at omega equals to 1.
1.
So if we put omega equals to 1, it will be just 1, so that is equal to 45 degrees. Okay, now consider a plant whose transfer function is a second order plant. We have 1 by s square plus 2s plus 4. What is the magnitude in dB of the low frequency asymptote in the magnitude plot? So first you have to find the low frequency asymptote and find its magnitude. Low frequency asymptote is nothing but as omega tends to 0, what will be the magnitude in dB of this transfer function? So that's the same question, just another written in another way. Let's write the transfer function in frequency domain. It is 1 by j omega square plus 2 j omega plus 4, which is equal to 1 by minus omega square plus 2j omega plus 4. So let's club the real and imaginary parts. It is 4 minus omega square and plus j 2 omega. Okay. What will be the magnitude? It is magnitude of numerator, it will be 1. Okay. And the magnitude of denominator, it is 4 minus omega square, square root of real part plus imaginary part. So it is nothing but 4 omega square. Okay. Now calculate it in dB and find the final value as omega tends to 0. P of j omega in dB, it will be equal to 20 log of p j omega, and if we calculate it, it will be 20 log of numerator is 1, so log of 1 will be 0, so we can directly write for denominator. So it will be minus 20 log of under root 4 minus omega square plus 4 omega square. Okay. Now put omega equals to 0 or omega as omega tends to 0. What will be the magnitude in dB? So it will be minus 20 log, so omega tends to 0, omega tends to 0. We will left with log of square root of 4 square, which is equal to minus 20 log of 4. Okay, and 4 is nothing but square of 2, so 2 we can take out, so it will be minus 40 log 2, and we know the value of 20 log 2, it is 6, so it is nothing but minus of 2 into 20 log 2. Okay, and 20 log 2 is 6. So what is the final answer? Minus 12.
minus 12.
So the answer is minus 12 dB. Okay. What is the corner frequency of this transfer function? So for second order plant, what is a corner frequency? How is it defined? So your P of S was 1 by S square plus 2S plus 4. Okay. What will be the corner frequency? Now what is the standard representation of a second order system? It is omega n square divided by s square plus 2 zeta omega n plus omega n square. Now here there will be any scaling factor also. So basically the denominator in standard form is this. And for second order plant, the corner frequency is defined as the natural frequency of the plant. Right? So for second order, because when you plot the Bode plot for a second order system, the change in the asymptote or the change in the slope of the Bode plot you will observe at omega equals to omega n, and that's how we define the corner frequency, the frequency at which you observe a significant change in the Bode plot in terms of slope, right? Or the point at which the asymptotes change. So for second order system or second order plant, the corner frequency is equal to omega, and that is the natural frequency. And what is omega n for this plant? So omega n square is 4, then omega n is nothing but 2 radian per second. Okay, so the corner frequency is 2. Okay, what is the resonant frequency for the same transfer function? The resonant frequency. What is the resonant frequency?
Omega r is equal to omega n under root of 1 minus 2 zeta
Okay,
square.
so omega r equals to omega n under root 1 minus 2 zeta square. So it is the frequency at which we have a maximum amplitude or the maximum magnitude of the transfer function. All right, and so let's calculate it. Omega n we already calculated, it was equal to 2 radian per second, and zeta, so for this to hold, zeta should be lie between 0 to 1 by 2, because then only this under root term will be positive. Okay, so always remember that for a second order plant, for a damped second order plant, the resonant occurs at frequency equal to this when zeta is between 0 to 1 by 2. Okay, oh sorry, 1 by root 2, no, 1 by root 2. What if zeta is not between 0 to 1 by root 2? In that case, your omega r, if zeta is between 0 and 1 by root 2, then your omega r equals to this formula. But if that is not the case, then your omega r is equal to 0. Okay, think it is 0 or it is omega n. I will check this part, but for this to hold, you first ensure that your zeta is lying between 0 to 1 by root 2. Okay, so let's see if zeta is between this value or not. Okay, so what is 2 zeta omega n for this plant? It is equal to 2, and omega n was also 2, so 2 zeta into 2 is equal to 2, means your zeta is equal to 1 by 2. So zeta is 1 by 2 means it is within the range or not? We got zeta equals to 1 by 2. Is it in the range of 0 and 1 by root 2? Yes. So yes,
Yes.
the zeta lies in this range. So our resonant frequency we can calculate using this formula. So omega r now it is equal to 2 under root of 1 minus 1 by 4 into 2 is 1 by 2, which is 2 divided by root 2, or okay, so 1.41 is the correct answer. Okay. Okay, so in this question we are given two transfer function. So system 1 is S, let's call it P1. P1 is S plus 2 divided by S plus 5, and your system 2, let's call it P2, it is 2 minus S divided by S plus 5, which is an incorrect statement. For these two systems, check which statement is false. So the first two statements are related to high frequency magnitude. So calculate the high frequency asymptote, magnitude of high frequency asymptote or high frequency magnitude of these two transfer function. So what can you observe for these two transfer function? The magnitude of these two transfer function will be same or different, because we have the poles at the same location, but the zeros are at the same magnitude, but one is on the LHP and another is on the RHP. Okay, now let's find out its magnitude. So it will be magnitude of j omega plus 2 divided by magnitude of j omega plus 5, which is equal to 4 plus omega square, and it is also equal to 5 plus omega square. Okay, for P2 we have to find the magnitude of minus j omega plus 2 and divided by magnitude of j omega plus 5. So it is under root 4 plus omega square and under root of, sorry, it is 25 plus omega square. Okay, so the magnitudes for both of them are same or different? They are same only. Okay.
Same.
Okay, now let's see the magnitude in dB, and as frequency goes to infinity, how the magnitude will change. Okay, so in dB, what it will be? It will be 20 log of 4 plus omega square divided by 25 plus omega square, and for T2 it is 20 log of 4 plus omega square divided by 25 plus omega square. Okay, so what will be the magnitude at omega goes to infinity? Now if omega is very large, what we can write? We can write it as 20 log. So if omega is very large and if we are adding a very small number 4 to it, so that is irrelevant. So the numerator will approximate it as under root omega square. And similarly, if omega is very large and adding 25 to it is irrelevant, so we can approximate it as omega square. Now it is an approximation. So both the numerator and denominator are equal. So we have 1. That means the magnitude will converge to 0 dB. And what about this one? So these are essentially the same because we have the same numerator and same denominator. So as omega tends to infinity, this for this case also the magnitude in dB will tend to 0 dB. Okay, so the first option was the high frequency magnitude of system 1 tends to 0 dB. So this is the correct statement. The second statement about system 2, the magnitude of this will also tend to 0 dB as omega goes to infinity. Now the third one is about the phase. So the high frequency phase value for system 2 tends to 0 and the high frequency phase value of system 1 tends to 0. Okay. Okay, from here, can you recognize which among these two systems is the non-minimum phase system? So observe the zeros of these two transfer functions and tell me which one is a minimum phase system. What is the definition of a minimum phase system? So for systems, if all the zeros are lying on the LHP, then such systems are called minimum phase system. Oh, I couldn't hear you. So let's see the phases of these two transfer function. So the phase of P1 will be nothing but let's see what transfer function we have. The tan inverse of omega by 2 minus tan inverse of omega by 5. Okay, and for P2 we can write it is 2 minus j omega, so it will be minus of tan inverse of omega by 2 and minus of tan inverse of omega by 5. Okay, now put omega tends to infinity, what will be the phases? So
First one is 0.
290 minus 90. Okay, so this is 0. What about second one? So it is minus 90
Minus
minus
180.
180, so it is minus 180 degrees. Okay. Okay, so for system, okay, okay, let me again share my screen. Sharing has stopped. Okay, my screen is visible. Okay, so for system
Yes,
1,
ma'am.
as frequency goes to infinity, the phase is 0 degree, and for system 2 it is minus 180 degree. Okay. Okay, so this last option is correct because at high frequency the transfer function phase goes to 0 degree, so this is correct. But for 2 it is going to minus 180 degree, so this is not correct. Okay. Okay. Okay, let's solve some more problems. So the question is, the Bode magnitude plot of a first order stable system is constant with frequency. The asymptotic value of high frequency phase for the system is minus 180 degrees. Okay, and the Bode plot, it looks like this. So here we have log f. Okay, so this is the magnitude plot, so constant. So this is the magnitude plot. Okay, so this is p of j omega in dB, and this is the phase plot. So this is equal to minus 180 degrees, and the options are, we have one left half pole, one left LHP pole, and one RHP 0. Are you able to see my screen? Think there
Yes,
is
ma'am.
it's
No, it's
visible,
visible,
but
ma'am.
it's
It's
not
visible.
live. Give me a minute, wait. Let me connect again. Okay. So the options are, we have one LHP pole and one RHP 0 at the same frequency. Option B is, we have one LHP pole and one LHP 0 at the same frequency. Option C is, we have two LHP pole and one RHP 0 at the same frequency. The last option is, we have two RHP pole and one LHP 0 at the same frequency. Okay, so the Bode plot is given where we have a constant magnitude plot, and the phase plot goes to minus 180 degrees as omega goes to infinity. Then you have to identify uh, the number of poles and zeros and their location. Okay, are you able to solve this problem? Okay. Okay, let's
No,
see
ma'am.
how to solve. Okay, so the first clue is that we have a constant magnitude Bode plot. So what does it mean when you encounter a constant magnitude Bode plot? That can only happen if you have no frequency term appearing in the magnitude. Okay, that means whatever the frequency is, the magnitude remains the same. Okay, then what can be the possibilities to achieve this? The one possibility is that, let's say the transfer function is pj omega. The one possibility is that the transfer function itself is constant. Okay, so the transfer function is itself is constant means what? Means our magnitude will be nothing but equal to k, and the magnitude in dB will also be constant because 20 log k will be some constant number. Okay, but this cannot be the case here. Why this cannot be the case? Because if you see the phase plot, if the transfer function was constant, then its magnitude plot will also be constant, and also its phase plot will also be constant. But here it's not the case. If the transfer function was a constant, just a constant k, then its phase of p will be 0 degree. Or if it was minus k, then its phase was 180 degree. It was also constant. It would have also be a constant degree. But here We are starting from some 0 value and then converging to minus 180 degree. So this option rules out. Okay, this cannot be the case. The transfer function is not a constant here. Then what else we can have? What if we have a transfer function such that we have so all the options are saying that the poles and zeros location are at the same frequency. Okay, so the one possibility is s plus a or s plus a. So we have a 0 at s equals to minus a and we have a pole at s equals to minus a. As per the question, at same frequency we have given one pole and one 0. Okay, then what will be its magnitude? Its magnitude will be, so we will replace s with j omega, so our magnitude will be a square plus omega square and a square plus omega square. Okay, that will be equal to 1, that is a constant, and there can be some constant term here that won't change our analysis. So in dB, magnitude of P in dB, so this term will be equal to 1 and multiplied with k. So the final magnitude will be k, and in dB also we would have log of k, which is a constant number. So this is one possibility where we have the pole, one pole and one 0, and both are at the same location. Then in that case also the magnitude will be constant, because the numerator and denominator magnitude will cancel each other and we will be left with a constant term, and its magnitude in dB will also be constant. So the magnitude plot in Bode plot will be a constant, just as given in this uh, just as given here. Okay, okay, so the one option is that we have one pole and one 0 at the same frequency. Can we have uh, uneven number of poles and zeros, like can we have two pole and one 0? We cannot have two pole and one 0, because if we have two pole means we can have a transfer function of this form. It will be k 1 0 and 2 pole at the same location. We can write it as like this: we have 1 0 at frequency minus a and we have two poles at frequency minus a, because that is the only option we have. So we have created one transfer function like this, and when you calculate its magnitude, will it be a constant? It will not be a constant, because then its magnitude will be a plus omega square and divided by a square plus omega square, because we have a square term here. So under root of square root is just 1. Okay, then it will be k by under root of a square plus omega square, and you can see here that the magnitude here is dependent on omega. It is not constant, it is a function of omega. Okay, so the magnitude is not constant if we have uneven number of poles and zeros. So these two options are for sure not correct, because these two options are saying that we have two pole and one 0, which is not possible to have a constant magnitude Bode plot. Okay, now another thing that we have to guess is the location, whether they will be in LHP or whether they will be in RHP. or what? That we can guess from the phase plot of the uh, transfer function. Let's see how to check that. Now suppose, so since we have concluded that we have one pole and one zero in the transfer function to have a constant magnitude Bode plot. So that we have let's say we have a pole at some point, let's call it a can be positive, negative, so that means we can have something at LHP or something at RHP. Okay, and let's say we have a 0 at a only because we are given same frequency, so the location will be same, but it can either be LHP or LHP. Okay, so let's say we have a pole at a and pole at 0 at a. Okay, and we don't know what is uh, uh, the plus or minus sign. Okay, then our transfer function s, sorry, let's call it b, because then if we keep both as a, because we know only the magnitude are same, not the sign, so let's call it a and b. So we have then the transfer function p given as s plus b divided by s plus a. Okay, so let's say this is our transfer function. We have a one pole and one zero. Now can you calculate the phase of p? So for that we have to calculate p of j omega. So it will be j omega plus b and j omega plus a. Okay, it will be tan inverse of omega by b minus tan inverse of omega by a. Now what will happen as omega goes to infinity? Because it is settling at minus 180 degrees as omega going to infinity. So as omega goes to infinity, what are the possibilities? This is given that this will be equal to minus 180 degree. And when this can be equal to minus 180 degree, how can we equate this term to minus 180 degrees as omega goes to infinity? Yes, when this
If
term is
B is
minus
negative.
90 degrees and this term is 90 degree, then their sum will be equal to minus 180 degree. And when is that possible? When B is negative.
Negative.
Okay, and A is positive, right? So we have generalized the transfer function as s plus b divided by s plus a. So b is negative means the 0 is on the LHP or RHP. No, see
LHP.
carefully. We have b as negative, so b is some negative value. Let's say b is minus 2. It is a negative value. So b is minus 2 and a is positive but same magnitude. So a is plus 2. So the 0,
RH.
yes, so 0 on
0 on RHP.
RHP and pole on
Whole
LHP.
on
Okay. So the correct option is option number A. Option A is the correct one. We have one LHP pole and one RHP 0. Is this clear?
Yes, ma'am.
Um, I have few more questions, but let's solve these questions in the next session. Or if you want, we can solve one more problem. Let's solve. I have two more problems. Let's solve in the next session. Okay. Okay, then let's meet next week to have more questions on Bode plot. If you have any doubt, you can ask, and you can try solving the assignment problems of week 9.
Madam, if these things are recorded, can you post it on the site
Yes,
so that
yes.
I can
In
download?
the Google Drive link, which is available in the Google Sheet, the PDF is uploaded there, and
Okay.
also the YouTube link will also be provided in the same folder. Yes.
Tutorial discussion.
Yes, yes, tutorial discussion will be
Tutorial
posted
discussion.
as a YouTube link to the
Okay.
folder. In the folder that is shared to you, it is there.
Okay. Right. Okay.
Okay,
Thank you.
thank you. Yes.
Bye.
Any question? Okay, okay. Bye bye.
No, ma'am. Bye, ma'am.